All right, so in this 21st lecture, I think it is 21, yes it is. In this 21st lecture, what I would like to talk about is how do you solve the sort of linear problems that you get out of the mixed Laplace, or let's say anything that has a block structure like we had talked about for vector value problems. Before I do this, I would like to mop up one topic that I didn't finish at the end of the last class. So if you looked at the results of step 20, we wrote this program, or we wrote the data in GMV format. GMV is not widely used anymore, so I would like to replace this by BTK format. And to do this, I have already set up step 20 in Eclipse, like I have shown you before how to do this. So if I go here, step 20 is of course a much larger program than the one that I showed you when we talked about how to set up things in Eclipse. So I would like to find in step 20 now the function that's called output results. So one of the things that Eclipse does very nicely is if I hit Ctrl-O, it's going to show me an outline of this program. You can have this outline over here in the right panel as well. So if you want to have it permanently, this is the place. So what it shows you is all of the header files, and then it's going to show you the namespaces, the classes that are defined, and so on and so forth. I like to do this from the editor window because I can use it with my keyboard. So if I hit Ctrl-O, it's going to show me the same kind of outline, but I can filter it now. So if I want to find the function output results, I can, for example, just start typing, and it's going to narrow down the list to all of the things that match this string so far. So output results appears twice here, once in the declaration of this mixed Laplace problem. So this is the declaration of the function. Here's the actual implementation. So if I go down here, this is where this function is implemented. So I'm going to change this to VTK format, and then do write VTK, save it. Okay. And then make run. So when I run this, then it should produce a file that is called solution.vtk, and that's the one that I'm going to visualize with visit. So I have solution.vtk here. I call visit. I call open. I'm going to open solution.vtk. And what I want to show you is, so for example, I can visualize the mesh, and I can add with pseudocolor, for example, I can show you the pressure. I haven't talked much about what the setup of this problem is, so the pressure will not mean very much to you unless you read through the introduction of step 20, but it looks like this. You remember we chose a discontinuous element of degree 0, so that means piecewise constants for the pressure, and that's of course what you see here, that the pressure is discontinuous between cells. I can choose a different solution variable. So instead of the pressure, for example, I can choose the variable u, and let me make this window a little bit bigger here so I can more easily choose this. So here, variables. U, that would be the x component of the velocity, and it looks like this. And you see, for example, that just like we know from the theory of the Rabiat-Thomas element, the x component of the Rabiat-Thomas element is continuous in x direction, but it is discontinuous in y direction. So you see this here, from left to right it is continuous, whereas from bottom to top it is discontinuous. And I can show the same thing for the y velocity, that would be component v, which looks like this. So this one is of course continuous in y direction and discontinuous in x direction. What I would love to do, of course, is I would love to show the velocity field as vectors. And so let me remove this one here again, delete. And I would like to show this as vectors. And unfortunately, Visit doesn't show me any option for vectors. And the reason is that I didn't describe in the output file that the u and v components actually form a vector field. So that is something that I need to change in the code. And we talked about this 2 lectures ago, how to actually do this. So I had to enter this piece of code that we called data component interpretation. If you go back 2 lectures, you will find that piece of code, and what I'm going to do is I'm going to add this here, and I'm going to steal this piece of code from step 20. So if you read through the documentation of step 20, I'm going to steal it from step 22. If you read through the documentation of step 20, what you will find is a reference to this place here. So I'm going to copy this whole piece of code. I'm going to copy this all here. So my solution variables are now called velocity. So there are dim components that are all named velocity, and there is one that is called pressure. And so I can get rid of this whole piece of code here. And then I need to add a piece of code here at the end of this function call to add data vector. That is going to look like this. So, as I say, you can find the essentially this particular function in step 22. So if I run this right here, it should hopefully produce an output file in VTK format that now describes that the first set of variables is actually a vector field. So let me go back to my visit window here, like this. I need to reopen the file, reopen, and now let's see what it offers when I click on add. So I want to add a vector, and there is now a variable called velocity. And so if I add this here and I draw it, what I get is a vector field. Let me hide for a second the mesh so that it becomes clearer. So you see that in this here, it shows the velocity field as little vectors that generally point from the left to the right. This is how we set up the problem. If you look at the introduction, you will understand that we prescribe a high pressure on the left and a low pressure on the right. So we have vectors that represent these vector fields here. They don't always coincide because the velocity field is discontinuous. At every one of the vertices you have 4 different vectors that start at this point, right, from every one of the 4 adjacent cells. So what visit does is it plots 4 different vectors starting at every vertex. Sometimes they are almost exactly identical, so you don't see a difference. Sometimes they're not, because the solution is discontinuous on these 4 different adjacent cells. So this is how I can visualize vector fields. We do this in a number of other programs too. So if you go to step 22, for example, then in many of the fluid flow programs later on, step 31, step 32, step 46, and so on and so forth, we essentially use this sort of scheme that we have to describe in output results which components together form a vector field, and then you can visualize it in visit, for example, as a vector field. Okay, so from there, let me go back to what I really wanted to talk about in this lecture, namely, how do you solve the linear problems that come out of this mixed Laplace? So you remember this was the equation that we wanted to solve. So it was a set of 2 equations in a set of dim plus 1 solution variables. You remember how we got to the weak form. You remember how we got to the bilinear form that defines these matrix entries Aij. Now, we can look at this somewhat more closely. So this bilinear form that defines the matrix was essentially a word-by-word description of how we actually translate this into our code. You saw that the code basically, if you replace mathematical symbols by their Latin letter representation, this is basically how you would write it in deal.II. So we describe this bilinear form in the code in essentially like we write it down here. But there's something else that we can do. So in reality, these shape functions that we have are not so that every shape function has a non-zero u component or has a non-zero p component. In reality, our shape functions are almost always constructed in such a way that some of the components are non-zero and others are in fact 0. So for example, in this particular case, the shape functions are either of the kind where the velocity part is non-zero and the pressure is 0, or the other way around. And this is something that we can utilize. So I don't want to go into detail of how you would do this when you build the bilinear form, but you can read up on this in the documentation module about vector value problems. So if you go to the documentation of step 20 again, or to any of the tutorial programs, if you go to the top, there is a list of modules here, and there is a somewhere in the finite elements here section, there is handling vector value problems. So there's a lot of documentation about how to deal with these sort of things. So much of the content of the previous lecture is actually contained in this page. So there is much more information here. Step 8 also takes a sort of different approach to dealing with this. I don't want to do this for the bilinear form. I like the fact that I can write the bilinear form in code just like I would write it in mathematical terms. But we can exploit the structure of these shape functions in a different place, namely when we talk about the linear system. So if you take this sort of form for shape functions for granted, that they're either non-zero in the velocity or in the pressure and zero in all of the other components, then one of the things you can do is the following. So let's say I'm considering the ith row of my matrix. Well, I get the ith row of the matrix by testing with phi I, right? But phi I, as I talked about, was either of U-type or of P-type. So if it is of U-type, then this thing is non-zero, and this thing is non-zero, but phi IP is 0. So if I is a U-type shape function, so then in this row of this matrix, in reality only these two terms are important. Whereas if I is of P-type, then this will be 0, this will be 0, and this will be non-zero. So if the ith row corresponds to a shape function that is of P-type, then we will get something that looks like this. And of course, I can do the same thing for the index j. So if, for example, j happens to be of U-type, then and I is of U-type as well, then phi jp will be 0, and only this term here plays a role. Similarly, for example, if you had that j is also of P-type, then actually this term would be 0, and aij would be 0 altogether, because both of the shape functions, both of these, either phi ip or phi ju, are 0. So one of the things that I can do in deal.II is that I enumerate my degrees of freedom in such a way that the first set of shape functions are all of U-type, and then the remaining is all of P-type. So when I do this, then I come out with a block matrix, namely the first set of rows of this matrix here are all constructed by these U-type shape functions, and then the second set of rows are all constructed by the P-type shape functions phi j. And because the i's and the j's are of course the same, if I have enumerated first all of the U-types and then the P-types, that means that I have the same kind of structure for the columns. So I get a block up here where both the I and j shape functions are of U-type, and that means that is produced by this block here, by this part of the bilinear form. Similarly, over here, the i's are of U-type, the j's are of P-type, and so I only get a contribution from this term here. So that's something like the gradient of the pressure. Down here, I get the divergence term. Down at the bottom right, both the i's and the j's are of P-type, and there is no term in my bilinear form where both the i's and the j's appear as P-type, so there's a 0 down here. So what we should do then is we should use this sort of structure that comes out of this problem in our linear solvers. So we need to somehow represent this structure in our code, and then we need to represent this also to the linear solvers. Now, it turns out that solving these sort of problems that have a block structure is actually, let's say, any of these vector-valued problems is typically much harder than if you just solved the Laplace equation. So for example, the matrix that we have here is indefinite. It has positive and it has negative eigenvalues. And it also has this zero block. So if you think, for example, of something like a Jacobi solver or an SSOR, in both of these preconditioners, you would have to divide by the diagonal element. That's, of course, going to be a problem if the diagonal element is 0. In other words, you can't use CG because the matrix is not positive definite. And you can't use one of the typical preconditioners like SSOR or Jacobi because it has 0 diagonal entries. And so we will have to really rethink our way of how to construct solvers and preconditions for this sort of thing. I will have a lecture at a later time where I talk about, let's say, a general taxonomy of how you approach the choice of a solver or preconditioner for general kinds of problems. What I would like to do here is a fairly simple approach. Namely, I would like to construct a solver that utilizes this block structure by block elimination. So before I do this, let me just very briefly mention this. When you have a block structure for the matrix and for the vector, in deal.II, we represent this by classes block sparsity pattern and block sparse matrix for the matrix and block vector for the vector. You've already seen this in the class declaration of the mixed Laplace problem in step 20 when we talked about this, the class declaration in the last lecture. So you can think of these block sparse matrix and block vector for all practical purposes. They act like matrices and vectors. So in particular, you can access individual elements of these matrices and of these vectors. So if you access the ijth element, for example, you get the ijth element of this matrix. But they have a block substructure, and that means that that these classes, block sparse matrix, for example, it offers you a function called block ij that would give you the ijth subblock. So for example, if you asked for block 1, 0, it would give you this block here where we store B transpose. If you ask for block 0, 0, it would give you the matrix here. So for all practical purposes, it looks like one big matrix, but you can get at the individual building blocks of it. So what do we do with this? Now, I mean, I can represent this linear system here as two sets of equations, namely m times u plus b times p equals f, and b transpose times u equals g. So this one big system here is, of course, exactly equivalent to these two linear systems here. And what I would like to do is I would like to multiply this first equation with m to the minus 1. I can show that m is in fact invertible. So I multiply this by m to the minus 1. So I get an equation that looks like this. U plus something times p equals f. There's an m to the minus 1 missing on the right-hand side here. It should be m to the minus 1f. And then what I can do is, of course, I have the second equation that reads b transpose u equals g. Well, I've just solved for u here. So u equals m to the minus 1f minus m to the minus 1b times p. I can place this in here, and I get a second equation of the form b transpose m to the minus 1bp equals minus g plus m to the minus 1f. So if I do it like this, I get two equations, namely this one here that contains only p, and when I've solved for p here, I can stick this in here and I get an equation only for u. So this is, I have just decoupled this system. This approach is called forming the Schur complement. So this matrix that I have here, bt m to the minus 1b, is called the Schur complement, and I'm going to denote it by S. I can show relatively easily that the Schur complement is symmetric and positive definite, and that's of course exactly the kind of problem that we can apply the conjugate gradient method to. So I want to apply the CG method to this equation here to solve for p. When I have p, I'm going to stick it in here, and I have the equation m times u equals f minus b times p, where m is again a symmetric and positive definite matrix, and I can apply the CG method one more time. So I get these two equations. The fundamental problem, of course, is that, well, so how do I actually get this matrix S? It contains m to the minus 1. M is a sparse matrix, so m to the minus 1 is, of course, in general, a full matrix. I cannot hope to ever represent matrices in the finite element context as full matrices. They're just far too big. I can relatively easily store a million by a million full matrix, a million by a million sparse matrix, but I cannot possibly represent a million by a million full matrix. So I cannot hope to actually multiply out b to the minus 1 m to the b to the minus t m to the minus 1b. It's just not going to happen. So I need to somehow represent this matrix S in a way that does not require me to actually form this matrix element by element. It turns out that in deal.II I don't actually need this. So in deal.II all I really need is that what we call a matrix is really an operator. I need to be able to apply it to a vector and get a different vector out of it. And so the question is, how do I do this? So in deal.II, one of the things that we do is, let me show you how these solver classes are actually declared. So the solver CG class is a template on the vector class. But then the solve function itself is again a template on the matrix and the preconditioner class. So it's not required that you actually stick a sparse matrix in here, or a full matrix, or a block sparse matrix. It can be any kind of object that you want, that you apply as the matrix here. And the same is in fact true for the preconditioner. So I'm not going to talk about the preconditioner in this lecture, but you can read up on how we construct a preconditioner for step 20 in the discussion of the step 20 program. The only thing that the solver CG requires is that the matrix and the vector class are compatible. That means that you can multiply this matrix by this particular vector type. So of course sparse matrix double can be multiplied by vector double if you take the deal.II classes. But in general, the CG method does not really care what you have here in terms of vectors and matrices. It could be anything, as long as you can multiply them. And then how do you represent this matrix multiplication, or this operator multiplication, applying it to a vector? We do this through a function that is called vmult. So this matrix, this type here, that the compiler replaces for matrix, must have a function that is called vmult, where the first argument is the output vector and the second argument is the input vector. This is one of the very few functions in deal.II where we violate the rule that the input arguments come first and the output arguments come last. This is a sort of a historical vestige. Of course, also the name of the function is sort of a relic. vmult stands for vector multiplication. Today we would probably call this apply, because it really means that you apply an operator to a vector. So what do you do with this? We want to represent this matrix S, this b transpose m to the minus 1b. And so if you look at this, what we do in step 20 is we declare a class that's called sure complement. Sure complement takes this big matrix, this block sparse matrix A, that has blocks m, b, b transpose, and 0. It takes it as an argument, and it's going to store it somewhere in one of the member variables of this class that I don't show here. And then it has a function vmult that has an output, so destination. The second argument is the source. And what we're going to do in this function, in essence, the code looks slightly different, is that we create temporary vectors that have the size of the source. That might actually not be true. I would have to check this. But then, so forget about the initialization of the size here for a moment. We create temporary vectors for temporary vectors 1 and 2. And so when we want to multiply a vector by b transpose m to the minus 1b, we represent this as 3 successive multiplications. So the first thing is we multiply out b times the vector. That's the most rightmost part. Okay, so if you remember, S was defined like this. So if we multiply this with a source vector, the first thing we compute is b times the source. Then we have to multiply with m to the minus 1 times what we got out of this, and then we multiply it with b transpose. So multiplying with b is the 0, 1 block of this matrix. It's the top right block. 0th block column, 1's first block, 0th block row, first block column. So we multiply our source vector by this block, and we get out temp1. Then we somehow need to multiply with the inverse of the 0, 0 block. That's the m block. I'm not going to talk about this right now. But so we take the result temp1, multiply with m to the minus 1, and put this into temp2. And then we're going to multiply temp2 by the bottom left block. That's the 1, 0 block, and put the result into destination. That is the application of the matrix S to the vector that we want to apply it to. And for the CG method, that is really all that is needed. So CG does not really care how we compute this, whether we have an element-by-element representation of this matrix. All the CG method wants to have is that it can give you a vector, and this vmult function multiplies it with this operator and returns the result in this destination, in this DST vector here. So this is how we implement this in step 20. So what we need to do, of course, is also we need to multiply with the inverse of m, and we need to come up with a way to precondition the Schur complement. I'm not going to talk about this for now, but I would like to show you this part, and I would like to show you how the code actually looks. So if you go back to step 20, when we go to the function that solves this, so essentially the code is here. So we need to first form the right-hand side of the Schur complement equation. That was, if you go back here, the right-hand side was this here, minus g plus m to the minus 1f. So we have to represent m to the minus 1 somehow. We multiply this with the right-hand side of the first component of these equations, and then we add to it. So this is this vmult here. Okay, we put this into temp, and we form all of this together into this Schur right-hand side vector. And then we have the Schur complement class that we initialize with the block matrix and with an object that represents m to the minus 1. M to the minus 1 was already used here. M to the minus 1 is actually a class of type iterative inverse. So iterative inverse, if you try to find this in this program here, don't really know where that is in iterative inverse. That is a class I need to find this, but in essence, iterative inverse is a class that offers a vmult function which solves with m. I'm running out of time, so I have to hurry a little bit. So when we do this, then we can pass the entire thing over to solver CG. So solver CG then takes this Schur complement object as its matrix, then solution.block1, that's the pressure, and the Schur right-hand side that we have formed, and then the preconditioner that we built. So this gives us the solution of the first equation. And then I can solve the second equation, where I just have to multiply with m to the minus 1, which I do iteratively. And what we have to do before this is that we compute the right-hand side of this equation, mu equals something, something, something times bp. So because my time is limited here, what I would encourage you to do is, if you want to read up on the details, go to the Step 20 tutorial program and take a look at how these classes are actually implemented. I hope that you got an idea of, let's say, how we represent these sort of operators and how we represent these matrices in deal.II, namely not as things that actually have matrix entries, but as things that can be applied to vectors. And that is really all that you need to do for, let's say, the CG or any of these Krylov space solvers. There are many applications of this in deal.II. Step 20 is only one, but you will find the same kind of concepts in many other places as well. So take a look at this and familiarize yourself with this.